Welcome to class 16 of dynamics. Here's the kinematics of rigid bodies, and we're dealing with rigid body acceleration. This is, warning, one of the most difficult, generally one of the most difficult topics for students. There's a lot to go on here, so we want to be very careful in our approach, not to be too worried about it, but we do want to be methodical and pick things apart. So just be aware. And because of that, I've dedicated 2 classes to it. Classes 16 and 17 are for rigid body acceleration. Generally, we would also have technically 3 classes. Class 18 would be a continuation where we include the Coriolis acceleration into the mix for rigid body acceleration. But that often gets dropped due to snow days, and in this case for spring 2020, because we had to shorten the academic year by 2 classes. But anyway, here's the bottom line up front. Kaboom. As you'll recall, for rigid bodies, we can define the motion as a combination of translation and rotation. And translation, and we usually do that by having this relative motion equation. For velocity, if we wanted the velocity of B, we took a reference point on the rigid body, call it velocity of A, and then we took the velocity of B with respect to A to be able to define the velocity of B. That allowed us to fully define what the kinematics were of the rigid body. And that velocity of B with respect to A in one plane in 2 dimensions was to be omega k crossed with r, the relative position vector, right there. For acceleration, we have something very similar, a very similar treatment. There are certain differences, but we still use that fundamental concept, that relative motion between 2 points, where we have a reference point, point A, and then we have the relative motion between them to fully define what the motion of B is going to be. And between that, we've now captured what the motion is going to be of the rigid body. That A can be broken down now into 2 parts. That's where this is different from rigid body velocity, rigid body acceleration. We have a tangential component and a normal component. And that in one plane, that tangential component is the angular velocity crossed with the relative position vector. And then the normal part is minus omega squared and the relative position vector. All right. So this is going to have a lot of physical significance, and it's going to be tied back to particle kinematics. So there's lots of things going on here, but you've already covered a lot of the things. We've already set the foundation for some of it. So that was the bottom line up front, and I'm repeating some things right here, but let's take a look at some of them in a different perspective. Right here, once again, that is the big idea. And once again, this is translation and rotation to define the motion of a particular point. And together, they fully define the motion of a rigid body. One way that we could approach this is to start from the position vector, right? So if we had the relative, the position of point B, and we wanted to find it based on a known position and then the relative position between the two, this would be true. We took the time rate change of that, and we get what we already know to be true here, what we covered already in the previous classes. But now, if you want, and we could break down that relative position vector this way right here. If we take the time derivative of this, we're going to simply the time derivative of this acceleration of the velocity here is just the acceleration, but we want to take the time derivative of this part right here. And because of the Did we say the product rule? Yeah, the product rule. We have to take both the derivative of omega and the derivative of RB with respect to A. So when we take the time derivative of the omega, we just get alpha. But now we take the time derivative of this, the second part, we need to multiply that first part and we get the velocity of the relative velocity right here. But we already know the relative right here, that relative velocity was equal to this. So we have omega crossed with omega right here. And notice that the parentheses apply right here. Now, this is a generalized equation, and it is true not just for one plane, but for 3 dimensions as well right here. So we want to keep that in mind. You might continue with your dynamics pursuit, and you would want to remember or have some recall that this was the 3-dimensional version of this example, of this problem. But for 2D problems, what we end up having to say in summary is that the acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A and the tangent and excuse me, I meant to write this, that we have alpha K crossed with the relative position of B with respect to A, and then minus omega squared R B with respect to A. We'll break these down and look at them a little bit more closely down at the bottom of the slide. And just to write this out, and by the way, this whole thing right there is the acceleration of B with respect to A. I wrote the generic expression. I want to keep it in mind. Maybe, no, I was going to write it a different way. I'll just write it the way I have it down. And I think I've already written this, actually. B with respect to A is the tangential, because that's what this is right here. B with respect to A, tangential, and plus, I'm writing this, A, B with respect to A, the acceleration B with respect to A in the normal direction, which is this. And you notice that I made that little brace right there. I covered that minus sign as well. That's important to recognize the physical significance of that minus sign. All right, and especially as it relates to particle kinematics, what we learned in particle kinematics. Which I probably, maybe I should write that down up at the top, right down particle kinematics, a refresher of what that equation is. I'll write it up here at the top, all right? Let's write it in another essay, say, recall. And for particle kinematics and polar, is that going to help us any? The acceleration of a point was going to be equal to the R double dot minus R theta dot squared ER plus R theta double dot plus 2 R dot theta dot E theta. Okay. Now, that was going to be when we had some kind of polar notation where we had R and we could have like an R dot term and an R double dot term as the whatever the thing was getting longer. In rigid bodies, the R's don't get longer, right? So there is no R double dot, and there's no R dot right there, right? So what we have right there is R theta double dot, which is in essence going to be this. Remember, theta double dot is the same thing as alpha. That's the R times there. So it's actually represented right here. You could see, tie that back into the particle of the R theta double dot is actually that angular acceleration times that relative position vector. And then remember over here, we have R theta dot squared. Well, look right here. We have R omega squared. Remember, theta dot is the same thing as omega and multiplied. And you notice they have that minus sign right in there. So these things are connected. They're just written slightly different. So coming back down to this generic equation, just looking at the thing, we want to recall that the tangential, this portion up here, is alpha k crossed with r b with respect to a position vector. And this portion right here is negative omega squared r b with respect to a. And as a practical term, this numeric value right here, you could just think of this as alpha r. And as a numeric value here, you could just think that as omega squared r. The significance of that negative sign right there. Notice that right here we have a scalar of r, negative omega squared right here, multiplied by a vector. So what that does is it takes that position vector, get back over here. It takes that position vector that's right, nope, sorry, that's what happened. Let's see if I can get back this over here. There you go. This position vector, which was right here, right? It reverses the direction because of that negative, so it's along the line and it's pointing towards the center, and that's why that's the centrifugal portion of it. That negative makes the position vector, which was pointing outwards, now it makes it point inwards right there. And then this cross product right here for the tangential makes this perpendicular to the position vector. And so that really is the tangential component and the normal component of these things. Notes there, if what would happen if the acceleration of A is 0 and alpha is 0? Would the acceleration be 0? Is there acceleration of B if the reference point doesn't move and it doesn't accelerate? Yes, there can be. If there is angular velocity, there is still going to be an acceleration at B because it's the normal acceleration, the centrifugal acceleration, if you will. Rotational acceleration has two components right there, right? So there's always two components. Look for them. Make sure that we notice that they are vectors. So if we break something down into components, we have the absurd problem we'll see coming up, that we have the component of the components, right? Or the components of the components. And that can be a little annoying. And then lastly, as a note, every time we do an acceleration analysis, we're going to also have to do a velocity analysis first. And okay, well, here was actually my slide where I was doing all that comparison to normal and tangential and polar coordinates. But I already talked about the polar coordinates, and we could see right here that this doesn't extend, and that doesn't, R dot doesn't exist, and R double dot doesn't exist. But by the way, in Coriolis acceleration, we bring them back in, and they do actually appear again. So that would have been class 18, just so you know. And then so that we would have a complete corollary here. But because this is rigid bodies and there is no extension between the 2 points, they're stuck together, r double dot 0, r dot 0, so those components right there. And you'll also recall that this right here, this dv dt, is the same thing as having a tangential acceleration. It's just, this is path coordinates where that comes into play. And we'll recall that v squared over rho is just another way to write omega squared r, because v is equal to r omega. If we were to square v, we would get r squared omega squared divided by r right there. One of the r's would cancel out, and we're left with this omega squared r. So just want to make this connection between what we already know. We like to use the 3-diagram method again. The difference here is in this diagram here gets a little bit more complicated because we're going to have 2 different parts to it. We're going to have a tangential and a normal component. We're going to have to break those down into pieces. So we almost always have to write out this equation and then say with some kind of known values. And a lot of times we will have to squeeze some things in here. We're going to have to know that some angles, and so is part of this, quite often it's going to be an angle like this right here, where this right here is going to be, let's call it phi, and that's phi right there, right? So we got an angle that's right in there. So we break this down into the x direction. It's going to be, and let's say that we happen to know, and by the way, we are writing this equation for this point onto the piece. So we also need to know an angle right in here, right? So, and we also need to know an angle right in here. So I called this one theta, I called this one beta, and this one is phi over here. So I write down that AB times the cosine of theta is equal to AA times the cosine of beta plus, and now we have 2 parts. Remember, we have 2 parts, and only the parts that are contributed to in the x and the y direction. So we're going to have alpha r, and I could call that RB with respect to A if I wanted to. I'll write it down small right there. And cosine of phi, right? So that's going, because that's going to be, let's see, I'll draw it in red right here. This part of the component of the thing. It's the component of the component. That's the hard part. The component of the component right here is that part right there. And then, and we notice that that is positive because it's in the positive direction here. But now we're going to have to go negative right here. Now, and that's not because of this negative. It's because we're looking at the diagram. And this guy right here has a component right here. Let me see. What can I pick? I'll go this light green. That part right there is in the negative direction, right? So I'll write it as the green right there. I could have color coded all these. And so that's going to be omega squared r times the sine of that phi, right? Because this is phi right in there, that angle right in there is phi. So we want to have that part of it, right? And then we do the y direction. And we take and we look, and we're looking at, from these diagrams, we're looking at the sign of these is based on which way the arrows are pointing, and we have to be careful when we need to make an assumption. We take a look at this, and the AB times the sine of theta is equal a negative, look at that, see, because it's going downwards. That component of AA is downward, so we put it as negative sine of beta, and then we take a look. We'll start with the tangential one, and we see that's a positive, okay, plus RB with respect to A. And generally speaking, we know that once we have the one above is cosine, it's sine, but we can also see that it's the vertical component is the opposite angle there, so the opposite side, so that is sine. And then we take a look at this guy, and it's going to be positive. Even though this was negative, that doesn't matter. What matters is what the arrows point to in the one above. And so that's going to be plus omega squared R, and I should have put a B with respect to A. B with respect to, wait, I say B with respect to A? Yes, okay, that's correct. Okay, sorry. And then that's going to be the cosine of phi, right? So things to know. We always begin an acceleration analysis with a velocity analysis. Quite often, the purpose is to get the unknown omega. Sometimes that's like the big key to the thing, is finding what that omega is. And we want to use we can use the acceleration vector equations with cross products built into them. I think I do that in an example. We can use the acceleration vector equations broken down into components using the vector diagrams, or the three diagram method, as I call it. You cannot use ICR. But just know that there is something that's analogous, but we're not going to use it, called an instantaneous center of zero acceleration, that gets used in some books. Now, what we haven't discussed as part of this yet are velocity triangles, and they are ugly. But we'll mention them, but we'll quickly say, let's not use those. But some books will try to use these and broke it down. By the way, I wrote everything I meant to write on this next page right here. Okay, so I wrote them out as components. I meant to wait till right there, so I should use that slide. Accelerations can be analyzed with the vector triangles, and that's a bad name. They're not triangles. They're got to be vector diagrams, because they're not triangles, or at least part of them is a triangle. But because this relative position right here, this relative acceleration, has two parts, they actually become quadrilaterals. They're not rectangles, unless it's a special case. We add in three parts to get the resulting AB, right? So we say that, yeah, well, right here, it's written out there. At AB, this thing that we want to know is made up of AA, right here, plus the tangential, I guess I'll do the tangential one first, right here. The tangential one and the normal one right here. Now, if you look and you see that these right here, they do form a triangle with this relative acceleration, because that does remain true. The problem with doing this is the confusing thing that they can cross, and they could do what we might call as a bow tie, right? That they don't necessarily make a open four-sided quadrilateral. They can make non-quadrilaterals, and that can be quite confusing to try to organize and put together. Not so bad if you were to keep them as triangles. Sometimes it might be worth doing, but for the most part, we're not going to do it, right? It's easier if you will draw out the relative the part that makes it into a relative acceleration, like this guy right here. Then this becomes the triangle, or this becomes the triangle, and even right here, right there, becomes the main triangle of the relative motion equation. And is that true right here? Yeah. this guy. And so looking at it that way, you can see that there's two triangles. A triangle superposed on a triangle. One of the triangles is the main one of the relative motion, and the other one is built off of that relative motion part that's built into into the tangential and normal. So they get confusing if you try to do it with triangles. So to avoid that confusion, we're not going to use the vector diagrams, the vector arrow graphics. Vector arrow graphics, that's a good way to put it right here. Instead, we'll use the 3-diagram method, or we could go ahead and work through the thing long ways using vectors. And I will do that in an example in the next video, because this one has already gone pretty long. So I hope you kind of got the basic idea. You might want to work through some examples, maybe come back and peek at this, and it'll cement the idea. Thank you, guys. 25 minutes is too long of a video.